Hello, my name is Alicia and this is my team. Now I'm gonna present about the forecasting energy demand. Before we discuss about the method, I'm gonna briefly talk about the data that we have analyzed beforehand. As you can see, these 2 days are representative of the general trend of the whole dataset. Even though that every day the energy consumption is different, it seems like there is a repetitive pattern for every 24 hours. Like you can see here, between 10 a.m. and 10 p.m., it shows the peak of energy consumption, and this pattern behavior is repeatedly seen in the whole data. So without further ado, let's go straight to the method of the prediction we used. This is the predictive pipeline, and we will start with the preparation first. The first thing we did is the persistence. The persistence will be the anchor for our test loss to beat. We tried the persistence for 5 hours ahead and 12 hours ahead, and the persistence for 12 hours ahead is higher than 5 hours ahead, which means that the accuracy for the persistence in 12 hours ahead is worse and easier for us to beat. The next thing we did is the normalization, which is really important to speed up our neural network to reach the minimum loss. And then we arrive at the windowing stage. First, we use a simple window, and why this is minus 19 is because, as you can recall, like I said before, this dataset have a repetitive pattern for 24 hours, and we are going to predict 5 hours into the future. So 24 minus 5 is 19, but it seems like this naive window doesn't really work well. So we try other features like standard deviations, mean, and difference, and it reduced the test loss significantly. Here, we are moving to the train stage. We are using 10,000 iterations to prevent too early stopping. Solver type here is Adam because it could stabilize the decrease of loss. We also tried stochastic, but it doesn't seem to work well in this case because stochastic gradient descent tends to detour in the minimum loss gradient instead of the minimum time itself, which is not good in this case, in some cases. After several training done, we found out that this data set test loss to be good enough, we need a quite large neural network size, which we decide to be 128 for the first layer. The input size is 29, dependent of the feature used explained in the previous slide. And for the perceptron in the inner product, the saturator used was the ReLU to speed up the arrival at minimum gradient. We also decided to reduce the neural network size of the subsequent layers by 2/3. The first layer should be larger because we wanted to capture the important information, and as we going deeper into the layer, we decrease the size to minimize the noise but still salvaging the important information. However, we took note that the last layer may not be too small because it could cause our ReLU value to become 0 and slow down the reaching of the minimum loss. Next, we use difference network, which is because much better than naive network. And the last part, we will visualize the predictions. As you can see, the actual and the predictions have a linear correlation, which means our prediction is good. Let's see the test loss. It shows that it's really easy to beat the persistence. The lag correlation also shows that the peak is at 0, which means that there is no lag in our prediction. Actually, if you see the leftmost upper graph, there's no overfitting, but we tried regularization to see if we can reduce the test loss or not. We tried dropout before, but the test loss seems to be increased. So we tried other regularization, which is L2 regularizations, and it turns out that the test loss slightly decreased and the lag correlation slightly increased. That's all for our discussions. Thank you very much.